Good day, Dr. Jala. We are presenting our renewable energy project titled Pavlov's Assisted Solar Output Prediction using a 2.4 GHz wireless link and low-cost weather sensing in a tropical environment. Let me introduce our members, which are Carlos, Rafael, Raymond, Yulong, and Kelvin. This project focuses on improving short-term solar prediction in tropical areas. In simple terms, we are studying whether a low-cost 2.4 GHz wireless signal can help detect rapid weather changes and improve solar output prediction. The main idea is to combine solar PV data, local weather parameters, and wireless signal measurements to create a more localized and responsive prediction method. After this, I will present the research background. Solar energy is becoming more important in Malaysia and around the world because it supports cleaner and more sustainable electricity generation. However, solar PV systems depend heavily on weather conditions. In tropical areas such as Kuching, the weather can change very quickly. Rainfall, humidity, cloud cover, and temperature can cause sudden drops in solar irradiance and solar PV output. This creates a challenge for microgrids because the power supply may become unstable if the system cannot respond quickly. Current prediction methods often depend on weather stations, irradiance sensor, satellite data, or large datasets. This method can be useful, but they may be costly, delayed, or not localized enough for small microgrid systems. Therefore, this project explores whether a simple 2.4 GHz wireless link can be used as an additional local sensing input for solar prediction. The main problem is that current solar PV prediction methods are not localized enough to react quickly to tropical weather changes. First, tropical weather changes very fast. Rainfall, humidity, and cloud cover can suddenly change within a short time, especially in Kuching. Second, when the weather changes, solar irradiance and PV output can drop suddenly. This can affect the stability of the microgrid. Third, microgrid control systems may react late because they usually respond only after the power drop has already been detected. Because of this, a low-cost local early warning signal is needed before the solar output reductions affect microgrid stability. This is where the 2.4 GHz wireless link becomes useful because changes in weather may also affect the wireless signal strength. The main objective of this project is to develop and test a localized 2.4 GHz Pavlov's model for solar PV prediction. There are three objectives. First, we will collect data. This includes weather data, RSI data, and solar PV data. Second, we will develop a model. The model will be a localized 2.4 GHz Pavlov's question for Kuching. Third, we will evaluate the prediction. This means we will test whether adding Pavlov's information can improve short-term solar PV output prediction. The expected outcome is a simple and low-cost sensing model that can support future microgrid prediction control. That concluded the introduction session. Next, we will move on to the literature review.
Thank you, Kelvin. My name is Lin Yulong, and I'm going to present literature review of our project. This section reviews the key literature that supports our project. The literature is built around three connected areas. First, solar PV output in tropical regions is strongly affected by strong weather changes such as rainfall, cloud cover, humidity, and temperature. These changes can reduce irradiance and cause PV power to drop quickly. Second, existing solar forecasting methods shows that solar output can be predicted using statistical, machine learning, and hybrid models. But many of these methods depend on reliable sensors, weather station, satellite data, or large data sets. Third, RF and microwave studies shows that wireless signals can also be affected by rainfall and atmospheric moisture. Therefore, this literature review connects these areas and leads to the main focus of our project, which is to test whether a low-cost 2.4 GHz wireless link can become an additional local input for short-term solar microgrid prediction. Now I will be explaining the weather impact on PV output. The three graphs compare cloudy, rainy, and sunny conditions. On a sunny day, the irradiance and output power are the highest and more stable. On a cloudy day, the sunlight is partly blocked, so both irradiance and power are reduced. On a sunny day, the output becomes the lowest because rainfall usually comes together with dense cloud cover, scattering and absorption of solar radiation. The most important evidence is that Hassan reported that rainy and cloudy days reduce average PV power by more than 93%, while irradiance dropped by around 80% during rain. This is very important for tropical microgrids because PV generation can fall very quickly if the controller only reacts after the power drops happen. Voltage instability may already occur. Therefore, the literature supports the need for an early warning or predictive signal before the output reduction becomes serious. These slides introduce the second main literature area, which is RF attenuation as a weather sensing method. When a wireless signal travels from the transmitter to the receiver, rainfall and atmospheric moisture can affect the signal. Raindrops can absorb, scatter, and reflect the transmitted wave, which can reduce the received signal strength and increase path loss. Previous studies have already used microwave links for rainfall detection. For example, 6 to 8 GHz microwave links have been shown to detect rainfall with an accuracy of at least 80%. More importantly, for our project, studies around 2 GHz show that low GHz radio frequency attenuation can still be measurable. As shown in the slide, the attenuation parameter increased as rainfall amount increased from 0.2 mm to 0.8 mm. However, one important caution is that 2.4 GHz is not the strongest frequency for rain detection. Because rain attenuation is stronger at higher microwave or millimeter wave frequencies, so our project uses 2.4 GHz mainly because it is low cost, available, and suitable for local microgrid monitoring. The slide reviews the existing methods used for solar forecasting. In general, solar forecasting is already a well-developed research area. The typical process starts with input data such as solar irradiance, temperature, humidity, wind speed, cloud cover, and rainfall. Then the data is cleaned and processed through steps such as normalization, missing value handling, feature selection, and data splitting. After that, different models can be trained to predict solar irradiance or PV output. Previous studies have used many types of models, including regression, RMR, RMAX, random forest, SVR, SGBoost, and LSTM. Machine learning is useful because it can capture non-linear relationships between weather variables and PV output. However, the main limitation for this project is that many high-accuracy methods depends on rich data infrastructure such as irradiance sensor, weather station, satellite data, scalar data, or large historical datasets. This can be costly, delayed, or less localized for a small tropical microgrid. Therefore, the design decision is to start with interpretable machine learning baselines such as linear regression and random forest, and then compare whether adding 2.4 GHz path loss features improve prediction performance. Research gap and project direction. From the literature, we can see that there are two strong research areas. On the PV side, weather reduce irradiance which lowers solar output. On the RF side, the same local weather event can also change RSSI and path loss along a 2.4 GHz wireless link. However, the gap is that most studies look at these two areas separately. Solar forecasting studies usually focus on weather data, irradiance sensors, or large data sets, while RF attenuation studies mainly focus on rainfall detection or communication link performance. There is still limited research that directly combines low-cost 2.4 GHz path loss attenuation with short-term solar PV output prediction for tropical microgrids. Therefore, our project direction is to collect weather data, RSSIs, and path loss data and PV data, then test whether adding path loss features improves the prediction compared with using weather data only. In simple terms, the project is not just about PV forecasting or RF rainfall sensing alone. It is about integrating both to create a more localized and low-cost prediction approach for tropical microgrids applications. Now I will pass my turn to Raymond to explain the methodology.
Hello, sir, I'm Raymond. I'll explain the methodology of this project. The main purpose is to develop a path loss assistant model to predict solar output power under tropical weather condition using 2.4 wireless measurement. So the first step is data collection of the humidity, temperature, rainfall, SSI, and the solar system voltage and current from the monitoring system. And step 2, convert the mentioned ISSI into the path loss in dB form. Step 3, the solar power is calculated by multiple the voltage and the current of the solar system. Step 4, after the data is obtained, it will be used to develop a regression model to study the relationship between the weather variables and path loss and the solar output power. And after this, the trend model is validated by using the live data and evaluate the performance using the RMSE, MAE, and R square. Finally, the trend equation is applied into the embedded system for the real-time solar output estimation. For the overall goal is to estimate the solar output power accurately by combining the 2.4 GHz path loss with local weather parameter in a low-cost monitoring system. So next, for the experimental setup and the hardware, the diagram shows is the measurement setup. The Wi-Fi router transmitter is placed far away to the receiver, signal receiver, and the sensor 42 meter. And for the hardware configuration, the transmitter is a TP-Link for in a 2.4 GHz operation, and the receiver is for the data logging and the ISI reception. For the temperature and the humidity measurement is using the THT22 sensor, and rain gauge is used for the rainfall measurement. There is also a solar array and also a voltage current measurement for the solar power monitoring. And so next, for the system configuration, there is the 42 meter for the distance setup, and for the solar array, there's total four solar cell that for each is 5 watt, 250 megawatt, mega ampere, and they are connected in series and parallel. For the rain output, for the rated output is total 10 volt, zero point 0.5 ampere, and total power output is 5 watt. And the low-cost dual purpose cell was developed to collect both wireless propagation and solar energy data under tropical weather conditions. So next, in the data collection process, the collected parameter included the humidity, temperature, rainfall, ISSI, solar voltage, and solar current, and also the consistent timestamp. For the data set, the whole data set, there will be split total 2000, around total 2400 data for the training data and 1000 and around 1500 for the validation data set. And the condition is tropical, and the environmental condition is tropical outdoor condition. For the collection node, data will log simultaneously from the wireless link and the solar weather node. ISI and weather data were paired with solar electrical measurement, and the record were used for the model training and the live validation. Note that all measurements are collected in synchronized form to support path loss and solar output modeling. Next, for the data pre-processing and the calculation. The raw data collected from the monitoring system will process and transform to obtain the required variables for the regression model development. The first step is the data cleaning. We will remove the invalid and the missing value, and then check all the sensor error or the outlier, and then ensure all the timestamps are consistent. Next, we will convert the mentioned ISSI into the path loss by using the equation path loss equal to 27 minus the ISI in dB form. And after this, the solar power is calculated by multiple the solar system, the voltage, and the current. And the maximum solar power is 5 watt. So next, the step 4 is the feature transformation. We will transform will calculate the humidity and the temperature in the square form and also the natural log of the rainfall plus one. And finally, we will combine all the data and split into the training data and the live data. So the expected output for this part is for the pre-processing part is the clear and synchronized data set. Derived variable included the path loss, the humidity and temperature in square form, square value, and the natural log of the rainfall plus one, as well as the power, solar power. And we expect that all the variable is in consistent unit. So next is the regression model development. So all the development of the path loss and the solar output equation is using the training data set and follow the polynomial regression method. So first is the path loss model. The objective is to model the 2.4 GHz path loss using the weather condition, include the humidity, temperature, and rainfall. And the coefficient is estimated from the training data set by using the least square regression. And after the model is estimated, it will be used for the solar output model estimation construction also. So the construction step is similar to the path loss model, using the least square equation to estimate the coefficient as well. And then the overall whole process is that the attempt the training data set and then do the feature preparation, and after this apply the least square equation to construct the path loss and the solar output model, and finally do the evaluation, validation, and then apply in the embedded system. And note that non-linear term were included to better capture humidity, temperature, and rainfall effect. Finally, we'll do the validation and the embedded system implementation. So in the validation, we'll use the ANSI live data for the assessment. And for the path loss and the solar model, we'll compare the measure and the predicted path loss data on the ANSI live data. So the result expected output is that the prediction follow the mains live data stream. The model generalized reasonably well to the ANSI data, and the validation are accurate. And in the validation process, the result is accurate. And after the validation is done, we apply the trend equation into the embedded system. For the input side, the measure input include the humidity, the temperature, rainfall, ISI, voltage, and the current. And then in the microcontroller, the ESP32 or the Arduino, you apply the conversion equation and the trend model regression equation also. And finally, display the measure input and the predicted solar output, which is the complete whole process and the function. And note that the trend equation was successfully validated using the ANSI live data and can be embedded into a low-cost microcontroller system for the real-time solar output estimation. And that's all for my part. Now I'll pass the presentation to Rafael.
Hello, I'm Raphael, and for this slide, I'm going to show the result of the weather-based path loss model. The aim is to understand how humidity, temperature, and rainfall can affect the 2.4 GHz wireless link. On the left side, the plot shows that the path loss increased with humidity and decreased with temperature over the measured range, and increased with rainfall in a logarithmic pattern. This means that the relationship here is not purely linear, but rather the model uses a combination of quadratic and logarithmic terms. The equation on the right shows that the trained path loss model, instead of me explaining every term one by one, the main point is that the equation uses humidity, temperature, and rainfall to estimate the path loss. The model was trained using 2,418 records and achieved a residual R of 0.9879 with an RMSE of 1.1273 dB. This shows that the model can capture the effect of tropical weather on a 2.4 GHz path loss quite well. The important takeaway is that path loss can be modeled as environmental variables, and this path loss value is later used as one of the inputs for the solar output prediction model. This slide shows the solar output prediction model. The purpose of the model is to estimate the solar power using a path loss together with a humidity, temperature, and rainfall. From the plot, solar power decreased as humidity increased, and it also dropped sharply when rainfall increased. Temperature shows a positive trend in this dataset, likely because higher temperature is associated with brighter daylight conditions. The last plot shows that the higher path loss is generally linked with the lower solar power. The equation on the right is the trained solar output model. The main idea is that the model takes path loss and weather data as an input and then estimate the solar output power. The model achieved a residual R of 98.93% and RMSE of 0.1312 watt. Since the solar array is only around 5 watt, the error is quite small. So the key point of this slide is that path loss is not the physical cause of the solar power reduction, but rather it works as an additional environmental indicator for predicting the solar output power. This slide shows the live validation data. The model was trained earlier and then tested using unseen live data containing of 1560 records. The top graph shows the full live dataset comparing measured solar power with the predicted solar power. The blue line represents the measured value and the red line represents the model prediction. We can both see clearly that the both of the lines follow each other closely. The second graph zooms into a smaller section of the data. This actually makes it easier to see that the model is able to track both the rise and fall of a solar power, including the short-term changes. The validation performance shows an residual R of 96.34% with RMSE of 0.241 watt. The error is slightly higher than the training, which is expected because this live data contains the new variations and the offset. But overall, this slide proves that the trained model does not only work on the training data but also estimate the solar power reasonably well on an unseen live data. This slide will summarize the overall findings of the project. The first finding is that the tropical weather affects the 2.4 GHz path loss, humidity, temperature, and rainfall. All show measurable relationship with a signal attenuation. The second finding is that the path loss model achieved a strong accuracy, meaning to say that the weather variables were able to explain the path loss behavior well. Now, the third finding is that solar output can be predicted using a path loss and weather variables. This supports the main idea of the project, which is a path loss assisted solar output prediction. The live validation also shows that the predicted solar output power follows the measured solar power closely, so the model has a potential for real-time monitoring. However, the model is limited to a tested 42-meter tropical setup and a small 5 watt solar array. If the distance, location, antenna setup, or solar cell configuration changes, the model should be retrained. Overall, this project shows that the 2.4 GHz wireless link can be used not only for communication but also as an environmental indicator to help estimate the solar power output under tropical weather conditions.
Okay, Carlos here. Thank you, Raphael, for detailing the model's prediction result. Next, I will summarize how our system compares with previous literature and present the final conclusion of this study. To demonstrate the novelties of our study, we benchmark our works against 5 representative RF and microwave atmospheric sensing studies. As you can see, most previous studies in locations like Greece, Korea, and South Africa use very high frequency. They are ranging like about 10 GHz to 40 GHz. And their primary application was rain monitoring. Among this literature, only Hanasha in 2018 is linked RF attenuations to solar estimation, but they also use 10 GHz commercial microwave links under a Mediterranean climate. In contrast, our research fills two key gaps. First, we utilize the 2.4 GHz ISM bands, which is absent from existing RF weather research. Second, we conduct our tests under equatorial tropical conditions right here in Kuching. The proposed model evaluates solar PV outputs for tropical microgrids, providing a highly relevant reference for this type of climate. Finally, let's move to the conclusions. The key outcomes of our study are very clear now. We are combining a 2.4 GHz path loss with weather variables and can accurately estimate solar PV outputs. We have validated this on around 1,560 unseen lifestyle sample and achieved an R-square of 0.989 and a low RMSE of 0.13 watts. Then why does this matter? Because tropical weather attenuates the 2.4 GHz link and cuts solar outputs at the same time. By deriving a path loss from RSSI, we obtain a low-cost, weather-sensitive extra predictor. Even more, the affixed coefficients run on an EXP32 or Arduino nodes without needing on-device retraining. It acts as a real-time estimator and time delay trigger for preemptive microgrids battery dispatch. And of course, there are limitations for our works. The current model is a site-specific to the 242 meters links and the 5 watts array. It requires recalibrations for new sites. In the future, we are planning to add irradiance and panels temperature sensors for stronger physical grounding. We also aim to benchmark against other machine learning models and test other distance, seasons, and panel size for long-term reliability. In conclusion, combining a 2.4 GHz RSSI derived path loss with a low-cost weather sensing is practical. Its accurate foundations for predictive solar microgrids control in tropical climates. That concludes to our presentations. Thank you for listening.